Ladies and gentlemen and distinguished speakers, welcome to the Geostrata's exclusive Geo Convo on just energy transition and promise of green hydrogen. We're gathered here to delve into a topic of utmost significance, the path towards sustainable energy and the role of green hydrogen in shaping our future. Today, we are honored to be joined by two eminent experts who bring a wealth of knowledge and experience to this virtual stage. Our speakers, Mr. Matthew Stevenson, who is a senior engineer at Advanced Materials Division, Mintek, South Africa, and Professor Amandeep Singh Oberoi, who is an associate professor at the Thapa Institute of Technology, India, both stand as beacons of insight and innovation. Hailing from the global south, they each offer unique perspectives on the challenges and opportunities that lie ahead on the journey to just energy transition in the global south. So the question is, why is the Geostrata holding this panel discussion? The main goal of this panel discussion is to bridge divide between the youth, the industry, and the academia of the global south, especially regarding the future of energy transition in this area of the world, with special emphasis on the green hydrogen technology. We want to motivate the youth of the global south to be equipped with scientific prowess and technological prowess when they move for advocacy of policy changes in the domain of environmental issues. We will explore the cutting edge advancements in the field of green hydrogen, a potential game changer in the quest for a sustainable energy future. Our speakers will shed light on the crucial role of technology, policy, and global collaboration in this domain. So, greetings, Mr. Matthew, and greetings, Mr. Amandeep. I'll be starting with my first and most basic question that most of the people will have is that if you could please enlighten us on how green hydrogen is different from gray or blue hydrogen. Is it only limited to the extraction methods or it is something else?
Okay,
Matt, yeah, go ahead. That's all right.
sorry.
Go ahead.
Yeah, so from my understanding, the real main difference is where the hydrogen is coming from. So obviously gray hydrogen is coming from a fossil fuel source, and in doing so, um, carbon gases are produced in the process of extracting the hydrogen. Green hydrogen, on the other hand, is using renewable sources as the energy sources. One of the most common being solar, and then electrolysis in order to extract the hydrogen. And in this way, the process is a lot more environmentally friendly. I think also one of the main differences at the moment is obviously the cost of production. So gray hydrogen is still quite cheap. We're talking about $1 to $2 per kilogram, whereas green hydrogen under good situations is about $8 a kilogram. So that's where our main challenge is for green hydrogen, is actually bringing that price down to a more competitive level.
So I can certainly add on this thing. Thanks, Matthew, for the nice, clarification on the gray and the green hydrogen. Now, beside the cost, the carbon emissions that are associated with it. I mean, with the gray hydrogen, the carbon emissions associated, obviously coming from the fossil fuel sources, it's huge. And the green hydrogen, there is no carbon emissions. In between the two, there is also the blue, or you call turquoise hydrogen, where the carbon emissions which are coming out from the fossil sources can be captured before liberating into the atmosphere in the process of generation of the hydrogen. Well, if you capture the carbon emissions while production of the hydrogen, that's what it is termed as blue or turquoise hydrogen.
So, Professor Ramandeep, while reading on this, when I was reading on blue hydrogen, there is something called CCS storage, which is like they use a different type of storage for like storing the blue hydrogen, which is produced from the specific like method. If you could enlighten us about that.
Thanks for touching the part of storage. See, hydrogen, the audience must understand it's not available in a free state on this planet. So it's always available as a form of a chemical compound, either CH bonding, that's carbon hydrogen bonding, or hydrogen oxygen bonding. So in order to get the pure hydrogen, you need to break this bond, which of course requires the energy. Storage, how it can be stored? It can be stored as a gas, it can be stored as a liquid, it can be stored as, again, in the form of a bonding. We call it as electrochemical storage. As a gas, in order to achieve intense or high gravimetric energy storage density, of course, we need to compress the gas, because any person who is compressing the gas, or any person who requires higher densities, need to compress it. And if you need to compress it, you need to spend energy. Same goes with the liquid. Hydrogen cannot exist in a liquid form at NTP, normal temperature pressure. It requires cryogenic temperatures. If you want to achieve the cryogenic temperatures, I'm talking about minus 273 degrees Celsius. Again, you need to compress the refrigerant, you need to expand the refrigerant, you need to expend the energy. Electrochemical, on the other hand, or solid storage, what we call it as, it does not require much of energy expenditure as compared to its counterpart, and it's more safe to store hydrogen in a solid compound as compared to liquid or gas. You don't have to bother about the leakage, because it's not liquid, it's not gas. You don't have to, it's less hazardous. That's from my side on the storage.
Yeah, thank you for that, Professor Amandeep. I think we have expanded on how the storage relating to hydrogen fuel cells goes about, because that is a very important part which much of the apart from the academia people don't know about. So my next question is, and I would like you guys to answer it in respect to South Africa and India respectively, is like, how do we see hydrogen, green hydrogen specifically, being a driver of sustainable energy transition in both of our in both the countries, and what are the some recent advancements that we have seen uh, in this technology? So Mr. Matthew, if you could begin first.
Okay. Yeah. So, in terms of South Africa, um, I think this goes for the global south and maybe even the globe in general. So one of the main roles that green hydrogen will play um, is of course providing a means of storing and transporting actual renewable energy, um, clean energy. So in this way, it can solve one of the major challenges we face in moving towards a sustainable energy future. Um, and that of course is the intermittency of our renewable energy sources, such as wind and solar. Um, so it can facilitate in that way a more extensive and efficient use of renewable energy, and reduce carbon-based emissions substantially. So in line with this, green hydrogen will also play a significant role in the decarbonization of industries um, in South Africa as well. And in this in this respect, it's more so at the moment for industries that are difficult to electrify directly from renewable sources. So this is industries, heavy industries such as steel and cement, and also transportation. In terms of some of the most promising breakthroughs that I've seen, there's been a lot of work done on developing specialized techniques for increasing the large-scale production of electrolyzers, and also boosting their overall performance and reducing requirements of one of their major catalysts, which is a big area of research, and that is reducing the requirements for iridium. So iridium, as we know, is quite a scarce element, um, and these devices generally require quite large amounts of iridium, which is also very expensive. So we're looking here at some quite innovative catalyst coating technologies that have emerged that significantly increase the efficiency of the electrolyzer while at the same time lowering production costs. And if I can give an example, Oxford Nanosystems Nanoflux technology, for instance, has shown some amazing results. So catalysts have also seen some major advancements One example is also iridium oxide nanosheets that have been developed that have actually shown a reduction of about 90% in iridium while still maintaining performance. So, and if I can also just say Hasa catalysis, which is where I work, we're also making some major strides in electrolyzer catalyst development and MEA fabrication techniques, which I won't go into too much detail. And we are in the process of also scaling them to production capacities, which is something that needs to be kept in mind with these developments as well. Thanks.
Yeah, so Professor, if you could delve into the same topic with regard to how we are seeing it in India.
Green hydrogen production primarily, using the renewables, using electrolysis. Yes, there have been some major breakthroughs. Yet there are challenges that are to be addressed in the field. The cost of the green hydrogen is high. The major reason is, as Matthew said, is the cost of the catalyst. We are looking for the reducing agents and oxidizing agents. For reduction, we are primarily relying on PGMs. It's called platinum group metals. If you talk about South Africa, I've mentioned this before as well. South Africa sits on 75% global reserve of PGMs, platinum group metals. As a result, the potential of leading the race in green hydrogen production with South Africa is immense. The only thing is, yes, how to increase the efficiency. When I say efficiency of electrolysis, we are primarily aiming for higher current densities across the cell and the hydrogen production rates. The major breakthroughs, as far as my knowledge is concerned, has been in the field of green hydrogen, particularly the AEMs. AEM is anion exchange membrane, which does not rely on costly platinum or iridium. They are using nickel, Raney nickel, iron nickel, which are comparatively less cheaper catalysts as compared to the platinum group metals. And we are getting some tangible uh, green hydrogen production rates. The only thing is the life cycle. It depends upon the end user requirement, what we are aiming for while focusing on the green hydrogen production. Are we aiming for the longer life cycle time of the electrolyzer that we are procuring, or we are looking for the higher efficiencies? Because these two things for now does not go hand in hand. If we aim for getting the higher cell efficiency, we end up investing more because there is no better reducing agent than platinum at this moment. And if we are looking for AEMs, which utilizes less costlier or alternate catalyst, but their life cycle is comparatively less. The efficiency is comparatively less. So, I mean, it depends upon the end user requirement, what we are aiming for. This is from the industrial point of view. So these are some of the major breakthroughs that I know in the field of green hydrogen production.
Thank you for that. I guess my next question was somewhat related to what you just spoke about, which is that what has been the main barriers. And like now I'll intensify the question. Is like what has been the what are the major barriers that you guys have seen has been in like the widespread adoption of green hydrogen as an alternative source? Like, is it only related to government policies? Is it related to some other technological capabilities we lack right now, or is it the public like the image of the public around it, like regarding the safety of the high density storage? I think Mr. Matthew can answer this first, and then we'll move to Professor.
Okay, yeah. So I think definitely in my viewpoint, one of the primary barriers is definitely very slow implementation of supportive government policies and regulations. That actually incentivize the use of green hydrogen by the various sectors industry, and that actually subsidize institutions aiming to establish green hydrogen facilities, such as through reduced land costs, tax breaks, and so on. In South Africa, we have something called SEZs, which are areas that are actually allocated for institutions to go and set up hydrogen production facilities, fuel facilities, and so on, where the land cost is substantially reduced, and there's tax breaks as well given in those areas. So that is something that needs to be adopted as an example more widely, and especially in green hydrogen's early stages. This not implementing these policies is just slowing everything down entirely, because the outlay costs are enormous at the moment. And so to get some momentum going, there has to be some assistance from government. So I think another barrier is also the maturity of the technology. So again, we have seen much progress that has been made in recent years. So significant advances in outright performance and also the longevity of electrolyzers. But we still need to see more in order for the economics to really make sense. So again, I'll emphasize that scalability when developing these new technologies needs to be beared in mind from the beginning. You can make the most amazing catalysts, the most amazing coating technologies, but if they are so complex that they just cannot be scaled to a commercial level, I think it's a waste of time to go into things like that. But yeah. So in terms of overcoming these sorts of challenges, especially in the global south, so again, government really needs to up their efforts and implement policies a lot quicker than what they currently are. So more funding definitely is a major issue, so that it can actually accelerate the advancement of the technology, and bring overall system and unit costs down as soon as possible. So some mechanisms could include international collaborations where knowledge transfer can happen, so that research institutions in the global south can leapfrog what has already been done, so that we don't make the same mistakes that have been already found in the more developed countries. And as you said, I think public and also industrial awareness is not quite where it needs to be. So campaigns to really highlight the necessity and advantages of green hydrogen is needed. So one avenue could be demonstration projects, for instance, which can be set up to show how these technologies work and what they bring to environmental uh, improvements. So yeah, I think from our side, that's some of the major challenges and what needs to be done in order to overcome them.
Yes,
So
Professor.
yeah, from my side, the primary barriers, I'll be specific. High technology costs. Hydrogen or production of hydrogen has always been, a costly affair. Lack of global supply chain. We are not connected well enough. There's no global supply chain, particularly in the field of hydrogen. I mean, there is a Europe which is running the hydrogen. They are constructing the hydrogen highway, and there is India or other global south countries which do not know about hydrogen to that extent. So lack of awareness about its benefit. Cost of renewable energies when linked with the hydrogen. See, hydrogen cannot be seen as a source of power only. It's a beautiful energy carrier. You can store, you can use it as an energy carrier. You can store the excess energy in the form of hydrogen instead of storing it in lithium, which instead is toxic and emit fumes. Then storage of hydrogen is too volatile. The, and then the industrial demand, as Matthew said, most of the industry is not ready to accept green hydrogen at the moment, owing to its cost and owing to the awareness, lack of awareness. Once it's done, I guess the government policies will change. The government need to change the policies quickly in terms of adopting the green hydrogen. And these are some of the major barriers that, or the hurdles that is pushing the technology backward.
Uh, Thank you, sir. I guess most of the issues revolve around the policy framework set forth by the government and the lack of awareness both in the public and the industrialists of the global south. And I think that has remained a major concern since the past. Any new type of energy transition that comes up in the global south, the public has like shown some apprehension to it. I think that has been a major issue in creating awareness. Sometimes it takes a lot of time for a government to create awareness among the people of the global south that okay, this is energy, this is a new form of energy, this is a new form of energy storage which we should move towards. I think I have seen that personally in terms of the adoption of electric vehicles in India.
Yeah,
I am astonished by the fact that people are finally accepting it. They're finally they are like they believe in the security of it. They believe in the idea of it, and that is the good path. That is a good path for both any country in the global south. So my next question revolves around is that how do like in the technology of high density storage that we use for hydrogen fuel cells, like what innovations do you see as the most promising for guaranteeing the safety and efficiency of storing and transporting hydrogen? Like, what innovations do you see are the most pivotal? If Professor, you could answer that first.
yeah, sure. See, I have came across, all types of fuel cells. If you're talking about the application of hydrogen and to use primarily as a source of production of electricity. But I would say the PEM fuel cell, the polymer electrolyte membrane fuel cell, is quite promising in terms of round trip efficiency if we are using the reversible fuel cell. When I say round trip efficiency, that means the efficiency that the electricity that we put in the production of hydrogen and the electricity that we take out from the hydrogen, from electricity in to electricity out. That's a round trip efficiency of the electricity. It's quite high if we are using reversible fuel cells, reversible PEM fuel cells. So I would again go with PEM fuel cell if someone asks me what type of fuel cell you reckon. It's most efficient fuel cell. It can work on NTP, normal temperature pressure, does not require high temperatures. The range is somewhere around 60 to 80 degrees. And that's why it's adopted commercially by the industry as well. The FCEVs, fuel cell electric vehicles, which are commercially available, they all are using PEM fuel cell instead of using other type of fuel cells. So yeah, from fuel cell point of view, this is the one. And from electrolysis point of view, again, it depends upon whether you are aiming for longer life cycle or you are aiming for high efficiency. Based upon that, I'll recommend two. One AEM, an ion exchange membrane electrolyzer, and another one is the PEM. That's a polymer electrolyte membrane electrolyzer.
Mr. Matthew, if you could just take forward the conversation.
Yeah, I mean, I think Professor covered most of what I also think is the case. Yeah, I think materials are a major challenge in developing high density hydrogen storage solutions. So at the moment, compressed hydrogen is the main storage. And so composite vessels are limited to around the 700 bar mark. So that can only store around 42 kilograms of hydrogen, somewhere around there, per cubic meter. So the storage density is still quite low. You need a large composite tank at a very high pressure in order to transport things. But again, they are relatively lightweight and strong. I also think metal hydrides, chemical hydrides, and porous materials, carbon nanotubes, MOFs, and so on, can give higher storage densities, but they do add weight. And also the reversibility of these technologies in terms of how much hydrogen you put in and what you get back, and then you have to revive the materials, is quite an issue. So, yeah, some of the promising technologies I see in this field, I think liquid organic hydrogen carriers, they show quite a lot of promise at the moment. They do, however, require catalysts for hydrogenation of the LOHCs and then dehydrogenation. And they also need heating and cooling. But for large scale operations, it could provide a promising solution. Yeah. I think in the future we're going to see a mixture of technologies coming through, and as time progresses, we'll start seeing the main ones stick their head out above the rest, and those will be adopted more so. Thanks.
Thank you for that. So, Professor Amandeep just spoke about how, like, the source material regarding hydrogen fuel cells, like, it is a very important factor. And my next question somehow revolves around the same, which is like, what do you think, like, how the level of impurities in the hydrogen feedstock, like, how does it impact the overall performance or overall efficiency of a fuel cell? And like, what are the some of the new technologies that are being worked upon to reduce this impact of impurities on the hydrogen feedstock? If Professor, you could answer that first.
Yeah, thanks for the question. Purity is highly important. Purity of the reactants. If you are aiming for some high efficiencies, conversion efficiencies. I'll speak again on polymer electrolyte membrane fuel cells. They are relying on some of the purest form of hydrogen to function properly. And when I say pure form of hydrogen, we are talking about 4-digit purity, that is 99.9999% pure. If you keep on reducing this purity, your poisoning or your fuel cell will not work up to the expected level of efficiency. And then another thing is, if the impurities are there, that's not pure, that can choke your GDLs. GDL is an inherent component of the fuel cell. It's called gas diffusion layer. The impurities, when they are diffused through the gas diffusion layers, they get choked if the impurities are there. Another effect is on the low MEA life cycle, membrane electrolyte membrane life cycle. Then the rapid consumption of the catalyst, reducing the overall life cycle of the fuel cell. So purity is something that we need to take care of the reactants. That's why it's never recommended to use the open air, depending upon the geographical location, if it's impure, for as a source of oxygen in the fuel cell. It's always recommended to check upon the purity before feeding it into the fuel cell. That will increase the life cycle of the fuel cell. That will give you the higher efficiencies. Same goes with the electrolysis as well. The amount of pure hydrogen or oxygen being produced depend upon the the purity of the water that is being fed in, the purity of the catalyst that is being loaded on the MEA, which is being used in the electrolysis. Okay, so purity is at most important if you are looking for some good results, some good outcomes. So we cannot compromise on the purity. Thanks.
Mr. Matthew.
Yeah, so I'll speak mainly from my experience. Uh, one of the main contaminants, if it's not an electrolyzer or green hydrogen source, is definitely CO, which is an enormously bad poison for platinum-based catalysts. So also in reformate feedstocks, you can see CO2, depending on how the cleanup has been done. And yeah, so the loss in performance in those cases when you're using platinum only catalysts is virtually, you lose pretty much everything, even with 25 or ppm levels of CO.
Yeah.
So to lower this impact, in our case, we use the platinum ruthenium catalyst, which substantially improves the performance of the MEA under the reformate feed. But also then requires quite a number of alterations in the way you prepare the anode electrode layer, which is where the poisoning takes place. So other common contaminants, sulfur, chloride, definitely. And as Professor said, these also clog up the GDLs because they end up adsorbing onto the GDLs, and that again reduces performance a lot. So the issue is that these contaminants also poison the platinum. They block platinum from adsorbing hydrogen, and that way the performance is reduced. So strategies besides substituting platinum ruthenium, we've also introduced an air bleed into the feeds, which helps in oxidizing the CO to CO2. And that also gives quite a marked improvement in performance. We've also cleaned up the feedstock before actually entering the fuel cell. And here we used a gold-based catalyst to actually oxidize the CO to CO2 before feeding it into the MEA. So yeah, that's of course green hydrogen mitigates all these problems. So yeah, thanks.
So what we have learned is that sometimes more than the feedstock, it is the quality or the impurities present in the water or the oxygen that is used. And as Mr. Matthew said, that one of the major source of the contamination or impurities is carbon monoxide, which he has said that they are solving by using a gold-based. Sir, if you could repeat that again, oxidizer.
Yeah, so if we want to clean up the feed before going into the fuel cell, we use a gold catalyst. But if we want to do the cleaning up in the fuel cell in situ, then we use a platinum ruthenium catalyst.
Okay, and which converts the carbon monoxide into carbon dioxide, as you said before. So thank you for that.
I'll share my experience on this as well.
Yes.
It's called CO poisoning, what Matthew is referring to as. I share one of the experience in my experiments. I've been working with the reversible PEM fuel cell, and we were not getting the expected results. When the fuel cell was opened up, we actually visualize everything. The GDL, carbon diffusion layer, carbon-based GDL we were using on the oxygen side or anode, it got eaten up by the CO poisoning. CO reacted with the carbon-based GDL, and its strands of carbon got eaten up. So instead of using the carbon-based GDL, now in order to mitigate this effect, we are using titanium-based GDLs, either titanium frit or titanium felt, which is far more stable than carbon-based GDLs wherever the oxygen or CO is available or on the anode side. So that's what my experience has been.
Thank you for sharing that experience. I think that will help both of you for future experiments and also the viewers of this conversation. So, my next point revolves around that we mentioned before is how do you envision hybrid systems being built around hydrogen fuel cells, which is how do they help in developing the overall energy infrastructure, the energy transport infrastructure in regards to the transportation of energy produced by renewable energy sources such as the solar energy or the wind energy. I've heard that it is a major part of the hydrogen fuel technology, which is transporting the energy produced. So if you guys could shed some light on it, Mr. Matthew, if you could begin first.
Okay. Yeah, so again, I'll just repeat, the intermittent nature of renewable energy sources is the major issue. So combining hydrogen fuel cells um, and these sources that can generate green hydrogen and then store it so that it can be used when needed. So that quite significantly improves the resilience of the overall energy supply. So the stored hydrogen can be converted to electricity during periods of high demand, and during periods of low demand, the hydrogen can be stored. And so that helps balance the grid overall if these systems are tied to the grid as well. What they do also allow is for more localized electricity production. In rural areas where it's simply not possible to provide electricity from the grid. So what's nice is they're clean, of course, and quiet. So it's not a big noisy generator that will be running in the background. Power to gas and gas to power systems also allow for quite an efficient use of available energy. So not necessarily from renewable sources, but during periods of low demand, standard coal-fired power stations can generate hydrogen, store it, and then through hydrogen fuel cells convert it back to electricity when the demand is high. So this still does have an environmental improvement overall. So this again will help stabilize the grid. So especially in countries where the likelihood of blackouts, where peak demands cannot actually be met by main grid's power generation capacity. which is an issue that I think most people know we are facing currently in South Africa as well. Some industry as well that stand to benefit from hybrid systems. Again, the hydrogen can be stored and then used to produce electricity via the fuel cell. The hydrogen as well can be used if high temperature heat is needed to actually be burnt and generate that high temperature heat. So we don't necessarily have to convert it to electricity first if the hydrogen can be sent through a boiler and generate heat that way. I think that's it from our side.
Professor, if you could go next.
Yeah. See, let's compare the two things. For now, the energy storage, we are relying on the lithium-based batteries primarily. Renewables or renewable sources, they are inherently variable in nature. They are not available 24/7 round the clock. So that's why there is a requirement of some storage device. Whenever there is excess energy available, which is or the demand is low, it's not peak time, and your solar PV or your wind or and so on and so forth, whatever renewable source of energy you are using, it's producing the energy. So we need to store it. If we are storing it in a lithium based battery, the problem is you do not reuse the energy which is stored in a lithium based battery. It will get self discharged by its own. You charge the battery, lithium based battery, do not use it for another 10 hours, come back and see the stored charge will be dropped drastically. They get self discharged in form of fumes, in form of ion deactivation. There are many losses, but they get self discharged. And let's compare it with the hydrogen based storage. The excess energy being produced by the renewables, instead of storing it in a lithium based battery, we are running an electrolyzer, we are producing hydrogen and oxygen, storing it as a gas or an electrochemical compound, whatever method you want to, and then it's going to be remain there until unless it is used next time. In other words, what I want to say is they are non-self-discharging technologies. The hydrogen and oxygen are going to remain stored until they are used next. Whenever the renewable is not available to produce the energy, the stored gases, the produced gases can be fed back into the fuel cell to generate the electricity. This increases the round trip efficiency to a greater extent as compared to the lithium based storages. Another problem with the lithium based storages nowadays is the recycling of lithium. It's costing more than its original mining cost. Nobody is ready to recycle the lithium. So at the end of the battery life, the lithium based battery ends up in the landfill. So eventually we are converting this planet into a lithium dump. So we can stop this lithium being toxic, emitting fumes. All these demerits of lithium based batteries can be covered or can be avoided by using the hydrogen based storages. As I mentioned earlier, hydrogen, although it has got the immense energy content compared to the fossil based fuels, but it must not be seen only as a source of power, but it's a beautiful energy carrier. You can store energy in the form of hydrogen, and then you can reuse it, and the efficiencies are quite high. Efficiency means round trip efficiencies.
So, to the audience, what Mr. Amandeep here is advocating is hydrogen-based storage devices in place of lithium-based storage devices. As we have seen, a lot of international conversation has been about how the extraction of lithium, or rather, and even the discarding of lithium batteries, has been an environmentally damaging process. And if green hydrogen is a promisable future in that way of energy storage, as Samandeep said, there is something regarding self-discharging of lithium batteries, which does not happen with hydrogen fuel cells, then it can be a very great alternative to the previous kind of technology that we use. So my next question is that how hard has it been for countries in the global south to set up large scale hydrogen producing facilities? Like what are some of the challenges that people are facing when setting up a large scale facility for hydrogen production? Mr. Matthew, if you could answer that first.
Okay. So yeah, so there's quite a number of challenges that are being faced. Um, so of course, setting up these facilities is quite a complex task at the moment, and it needs a lot of multidisciplinary collaboration. Um, and at the moment, the skills aren't necessarily available in all these countries just yet, or not established well enough at this point to really kick these facilities off ground. Um, so what I think how these challenges can be addressed. So I think what needs to be done at first is to actually really look at what renewable energy source would be the most practical in each country. Um, so a lot of countries such as India and South Africa, we've got a lot of solar power.
Yep.
So it makes a lot of sense to focus um, probably the majority of attention on that technology rather than trying to utilize every single renewable source that is available. Try and get the majority of your focus on the source that is most prominent in that country. I think that would have the most benefit rather than if you don't have a lot of wind, don't focus on wind. If you don't have a lot of hydropower, don't focus on that either. Um, Another challenge is, of course, the actual conversion efficiency of the technology that you're using. So you've got to look at the real viability of using whatever technology you're going to use. So if it's advanced electrolysis technologies like solid oxide electrolysis cells for improving efficiency as much as possible. You've also then got to look at is that technology actually financially viable? Um, Energy storage, yeah, you've got to carefully select which technology you're going to use. Um, Again, based on how effective it is and um, how practical it will be to actually store the green hydrogen that you're producing. So yeah, so again, the high upfront costs is the major challenge here. So for the global south, I think we need to look at funding from international finance institutions, setting up um, bilateral partnerships between nations, and trying to get private sectors involved as well. So this is where that awareness again needs to come into play, and then government really also needs to actually put policies in place that force industries to start including green hydrogen into their energy mix. So it's not to say all of it has to be straight away, but maybe 5% in for the next 2 years, and then can slowly increase with time. I think that's quite important as well. Yeah, again, also a lack of infrastructure at the moment is a big problem for green hydrogen. So collaborations are quite important in order to get knowledge of what mistakes have been made and what is the best way forward. Thanks.
Thank you for that, Mr. Matthew. Professor Amandeep, if you could continue.
Yeah, sure. We're talking about setting up the large scale hydrogen production facilities and the major challenges. Of course, running a single cell is far more easier than running a stack. When I say stack, you need to stack the number of cells in series or parallel, depending upon what voltages and what output current you're looking for. Setting up a new plant, the hydrogen generation plant, has always been costly affair. The one time or the what we say the capital cost is quite capex, we call it as capital expenditure, is quite high. The running expenditure depend upon what type of technology are you acquiring. As Matt said very clearly, depends upon what country you are located in, what renewable source predominantly is available, that is feasible. if you intend to generate green hydrogen, or if we are talking about setting up the hydrogen refilling stations, then Shell company have already set up a new refuel station in England, somewhere in UK. They are using the grid electricity instead of using the solar. Even you can think of using the grid electricity in order to generate your own hydrogen domestically at the site, instead of transporting the hydrogen through a pipeline or through the storage tanks. Setting up of large hydrogen generation plants requires some grave skills. The level of skills that are being developed at UG level, undergrad level, or at PG level are not to the mark which can design, which is required to design a large scale hydrogen generation. I mean, let me take the example of my own country, India. How many colleges in India are taking up this subject of fuel cell technology? I mean, in my home country, in my home institute, I'm the first one who have started this course on fuel cell technology, just to impart the technical skills, technical know-how about the this particular hydrogen fuel cell or electrolysis that is required to the UG students. Now, commercially available fuel cells or electrolyzers, the companies, those who are providing, they have got the monopoly across the globe. They are supplying. I know the companies which are the key ones who are supplying the electrolyzers and the fuel cells. But let's not stick to only those countries. If we are able to disseminate the skills, the knowledge across the world, particularly the global south, I guess we'll inculcate more skills among. We'll be able to produce industry fit engineers that are required to set up such plants that we are talking about, the large scale hydrogen production plants. And this could be the way forward towards towards producing the skilled labor. So this is one of the major challenges, that the awareness, again, as Matthew mentioned already, the lack of awareness. We have to break through that. We must spread the awareness about the subject.
Even I concur with that, sir. I come from a technological institute in India as well, and the lack of awareness regarding hydrogen fuel cells, or per se even fuel cell technology, has been very less for undergraduate students. And that has been a case with a lot of global south countries, but that is something we should work upon in the future. So, this is a personal curiosity question. So, like, when I used to read about electricity or grids 2 or 3 years back, I used to have this term that the grids of the future would, would not have singular input or output points. Everybody will be able to consume energy, everybody will be able to produce back energy and put it into the grid. And from what we have been following upon, a lot of countries in the West and a lot of developed countries have already started with this infrastructure, where you can, for example, set up a solar energy plant at your own home. You can use that energy, and if you have excess of it, you can put it back into the grid, which has the multiple entry, multiple exit point, or the bifocal kind of grids. So, how far has that technology been inculcated into grids of the global south, per se, India, South Africa, and how good the response has been? Because in the West, the response has been uh, even greater than what the public policy makers there expected. So, Mr. Amandeep, if you could answer that first.
Thanks for the question. I mean, we have to understand this thing. Having a multiple source of generation and unanimously putting the energy back into the grid is a source of generating reverse harmonics as well in the grid. The grid need to be stabilized at the same time if the input energy is coming from the multiple directions. We need to understand. Being an end user, we only know how to draw the electricity from the grid, but feeding in the grid with the electricity from different direction is a whole new subject. Once you feed it back from a single direction and there is a single direction of going out from the grid, there has to be a generation of reverse harmonics that need to be stabilized before we allow the electricity coming on from a different direction or going out from a different direction. It is possible, yes, but the grids has to be made capable of that. The current national grids, I'm sorry to say, in the global south, they are not capable of accepting the energy from various direction, and letting the energy go out from the various directions. But having said that, it doesn't mean the grids cannot be made capable of. The same grids can be made capable of accepting the energy from the various direction or from various sources. I talk about my own home. I've got a 5 kilowatt solar rooftop installed at my own home. The electricity that is being produced by the solar PV, I'm making use of solar, is being fed back into the grid through a bidirectional meter. I'm not using directly the electricity which is being produced by the solar PV on my rooftop. I'm drawing out the electricity from the grid. So the amount of electricity that I draw from the grid and the amount of electricity that I feed in into the grid, that gets subtracted, and this is what is called net metering. As far as India is concerned, this system is quite popular. It's called net metering system. Similarly, if this net metering is on solar, for solar PV, it can be for the various renewable energy sources as well. However, I come from the place called the northern plain areas of Himalayas, where the wind energy is not quite prevalent. It's not quite active. The solar is. We are making use of solar. But if there are multiple sources which are available, renewable sources to generate electricity, why not? We must make use of all the available resources, and we must be make our grids capable of accepting the energy from various directions. It can be done, but again, there is a lapse in the policy. The decision makers, the policy makers, have to orient or themselves towards making the grids capable of accepting the energy from various directions. It can be done, yes.
Thank you for that. So, Matthew, if you could answer the same question with respect to South Africa.
Yes, yeah. At the moment, South Africa also doesn't have the capability of multiple entry points into the grid. So, with our current load shedding situation, we have quite a large, uh, widespread adoption of solar energy panels around on people's houses, and they use this to charge a battery bank. But once that battery bank is charged, solar energy is essentially wasted. In most instances, some people can power their entire homes and are disconnected from the grid. Um, but there certainly is a large demand, especially now, to be able to feed back into the grid when um, the energy isn't necessarily needed at the house. If during the day when people are at work, for instance, at their offices, the solar panels are generating electricity, charge the batteries, and then the rest of the energy is just wasted. So, as Professor said, there's a lot of work that needs to be done in order to convert the grid to be able to do this. But it certainly can be done. I think uh, a lot of countries are just trying to um, sort out their normal ways of supplying electricity before you start looking at these more advanced ways where we can tie into the grid and reduce our grid electricity costs by feeding back.
Thank you for that, Mr. Matthew. It really helped me a lot when you guys answer this question, because some of the ideas in my mind might not be so ripe. Like as Matthew said, it is a major issue in countries of global south that we're not even able to reach areas where we should reach, and bidirectional grids or multidirectional grids are a thing of the future, at least in the global south. So my next question is that how do you guys view hydrogen being a major thing in achieving global sustainability goals? And what are some of the strategies which the countries in the global south should adopt specifically to not lag behind in this race, as we have done in the past few decades regarding other technologies? Professor, if you could answer that first.
Yeah, sure. See, the policymaker, the decision maker has to come forward to accept hydrogen as the fuel for future. The global economies or the economies across the globe, they have started accepting it, but it's still in talks. Until unless they feed us, the researchers, with the funding, some key results could be deferred. We do for what we are aiming for is to obtain the sustainable hydrogen economic goals, what is required is to bring down the cost of hydrogen generation. For that, the research is required. That cannot be done without R&D. And for R&D, we do need the funding and the facility. Until unless the funding and the facility is being provided to the researchers, it's just the talks that we are having to see hydrogen contributing towards the sustainable development. It has got immense potential. Each and every one across the global south and across the globe must realize the potential of the hydrogen, what it can do in terms of sustainable development. It's a beautiful, beautiful element of the periodic table. Its atomic weight is 1. It's quite lightweight. It's already been used in the space to power our space shuttles. We cannot use it we can use it on Earth as well, but the only thing required is the continuous research to bring down its cost and to improve its efficiency, which calls up for the collaborations, which calls up for the fundings and the research facilities across the globe. And the policymakers, they must come forward to accept it. Thank you.
Yes, Mr. Matthew, if you could answer the same question.
Yes, yeah. Adding on what has already been said, yeah, I also believe it will play a major role in achieving global sustainability goals, green hydrogen. I think one of the additional exciting roles it can play in countries in the global south that have substantial renewable energy sources is in the export of green hydrogen, which can improve the economic standing of the country as a whole. In a lot of countries in the developing or the developed world don't have sufficient renewable energy sources to power the country entirely. And so I think exporting will be quite an exciting role that it can play, in achieving also global sustainability goals, but improving the economic status of the countries where they are produced. And, definitely South Africa and India can stand to benefit in this way. I think another role has already been mentioned in some ways, that both the green hydrogen and fuel cell industries can create a lot of new jobs for people. A lot of countries in the global south are suffering with low or with high poverty numbers. And so this can create quite a number of new jobs for people in manufacturing, research, infrastructure development. So there's a number of areas that these technologies can have an effect on job creation. Yeah.
So thank you for that. I guess a lot of it is regarding the policy which are set forth in the global south, especially the collaboration which should happen between the countries of the global south, India, South Africa, and many other countries who can join their hands, and maybe even pooling resources if they want, regarding some specific technologies which are developed. There could be exchange program for students if we have some specific courses, for example, in South Africa or in India, which can help the undergraduate or the postgraduate students in both the countries to learn more about the technology. So I think my questions end, but if you guys have something very important, something very fascinating to share about the green hydrogen fuel cells technology, or even the sustainability goals, or how the energy transition is taking place in global south, I think the floor is open. So Mr. Amandeep, if you have any final words.
I would love to touch upon your concern, Vaibhav. See, this is I'm talking about through your channel. I'm going to, open up my own YouTube channel, particularly on hydrogen fuel cell technology. The dedicated course has already been implemented in my home institution. I want it to disseminate to across the globe. Whosoever is new to this field and want to know about the basic terminology and how it works, what hydrogen is, how it is used in fuel cell, how it is generated, so on and so forth. he or she can join and can find out the lectures on my YouTube channel. I'll definitely share the link on the Geostrata.
Thank you, sir, for that. I think we can do a work in it, amplifying your voice in the youth uh, as far as India or the global south is concerned. Mr.
Definitely.
Matthew, if you have any final words.
Um, yeah, I think also for people who are watching that are planning or interested in entering this field, it really is an exciting field, and there's multiple disciplines that are needed in this area. So, chemical engineering, mechanical engineering, chemistry, physics, uh, a lot of science opportunities available in this field. So, I really encourage people to give it a go and start looking more into these areas. Um, what is very important, I think, just for um, in general for the global south is that there's always this long-term strategy in place, so that our vision isn't just focused very narrowly on what's happening right now, but that we can see where we actually want to go. Um, so, and I know there are a lot of these plans being put in place by government and other institutions, private and public. So just from my perspective, like in South Africa, we have something called the Hydrogen Society Roadmap. And so this is targeted at guiding our country's transition towards a lower carbon energy system. Um, and again, leveraging our significant renewable energy resources for hydrogen production is the main focus. So here we have key milestones laid out, strategies and actions that need to take place in the country. And it also looks at distribution, storage, utilization in the various sectors within the country. And this is planned for the next 10, 20 years. Uh, and this sort of vision, I think, is quite key in in really uh, advancing and implementing these technologies in our countries. Thanks.
Well, thanks to both of you. I think policy changes, student exchanges, as Matthew said, setting a plan for at least 10 years or 20 years in future is what matters a lot for especially the countries in the global south so that they don't lag behind the West or the developed countries. So with that, ladies and gentlemen, as we draw the curtains on this enlightening geo convo, we extend our heartfelt gratitude to Mr. Matthew Stevenson and Professor Amandeep Singh Oberoi for their invaluable insights into the realm of just energy transition and the boundless possibilities that green energy and green hydrogen offers. The expertise has illuminated the path forward, reminding us that sustainable energy solutions are not mere ambitious goals, but achievable realities for the global south. Thank you, our esteemed speakers, and thank you all who have joined us in this enlightening discourse. Until we meet again to explore the new horizons of knowledge, let us remain steadfast in our pursuit of a better and a more sustainable world. Thank you. Thank you, Mr. Matthew. Thank you, Mr. Ramandeep.
You're welcome.
Thank you very much.